At the recording. Welcome everyone back. Thanks for being here. I can talk again. So we're good to go. How is homework 3 going? Any questions that I can answer about that right now? Not right now? Due Monday. Less challenging than the others, but still not nothing. Getting the screen share going for the Zoomers, although I'm not yet using it. No questions? Okay. Then fine. We've got the TAs and myself to help you as needed. I'll be checking email over the weekend if you run into any problems, and I have office hours on Monday for any last-minute problems. How's that sound? Fair enough. I'll let you know when the next homework is available, but it will not be for a little bit yet because it's about counts, which we are still working on. So how about we come back to count land here? I'm in lecture 3, slide 11. Yes, I agree. Yeah, my eyes don't work, but my ears do. They're the only thing that works with factory settings on me at this point. So we need to talk about distribution fit. Oh, I'm still muted. Thank you, Zoomers. I have started, and I was asking about homework questions. So do any of the Zoomers have homework questions? I was muted over break so I could talk to folks. Okay, doesn't look like it. So we've got then distribution fit to talk about. So we're talking about counts, right? Count outcomes this time. Counts have only a lower boundary. So what kind of link function do we need for counts with only a lower boundary? Log, as opposed to logit, which is the log of the odds of the probability of a 1, which is used for 2 different boundaries instead. There are other link functions that you may occasionally see for count outcomes. Inverse is one, like 1 over it, but I hate that one. That makes my head hurt. So we're not going to do that. We're just going to log. That means that the model scale directly predicts the log of the expected count, and if we want to get back to the regular expected count in terms of data scale, it's e to the prediction. So we're just exponentiating slopes and intercepts the same as we did before. And the TV is flickering today. I don't know if it's going to last or not, but if not, I'll just turn this screen around and we'll make it work. How's that sound? Yeah, we're just going to make it work. That continues to be the theme. So in count land, which is where we are, the link function is pretty well set. We're just going to log it no matter what. The distribution is the question. So up to this point, it was the opposite. We were trying to decide which link function we wanted, whether an outcome was ordinal versus nominal. Those are different link functions. And at this point, we're concerned about distributions instead. So I need to introduce, I don't think we've talked about this yet, a new idea of conditional distribution fit. The idea is each of these distributions makes statements about the mean and the variance. For instance, do you remember what's special about Poisson with respect to mean and variance as a distribution? They're the same. It has one parameter, and the mean and the variance are the same. So that predicts, if you think of like a scatter plot around a regression line, like it gets bigger as the mean gets bigger, which is what often happens. And the comparison that we might consider, we looked at before, negative binomial. Do you remember how that one adds something? I'll take a gesture, a letter, words. Anything you got? K is my notation. What does K do? It's a constant.
It makes mean bigger than variance.
I'll say it the other way around. Right idea?
Variance bigger than mean.
Variance bigger than the mean, yeah. So negative binomial, here's a picture for that. It has this variance function on slide 9 here, where the variance is supposed to be the mean plus the mean squared times k. So it allows the variance to exceed the mean in a quadratic fashion. There's linear fashions too, but research says this one works better. So I call k a stretchy factor. Essentially, it takes the variance and kind of spreads it out, and it results in distributions that have some degree of expected positive skewness, like this one here. So we have these two alternatives, but how do we know if they actually fit is the question. And this is not a question we can typically answer if we're working with normal distributions, which are a different family, or binomial or multinomial. We know they're okay. So here is something new that we're going to start paying attention to. So it's known as conditional distribution fit, and there is a statistic built out of the residuals in your model that is called Pearson chi-square over degrees of freedom. And you're like, is that the same words that I already know from some other thing? Yes, it's the same words, but this is a different thing. My apologies. In this measure, 1 indicates good fit of a distribution to a variable. And how it is computed is by summing over persons, this term right here squared, where the numerator says how far off the prediction is from what you actually got. So y in the data scale minus the predicted outcome, mu, in the data scale for each individual, divided by what the standard deviation should be at that prediction point according to the model. So it's sort of like, how much difference do you have in the data versus how much is expected by the model? And to the extent that the numerator is larger, that's over dispersion, meaning you have more variance than what the model is anticipating, and that means your standard errors and such are all going to be too low.
I'm
Yeah.
sorry to interrupt, but
Sure.
I am getting confused with the idea of making that fit. So
Yes.
what do you mean by fitting?
Fitting.
Now I got Poisson and negative binomial has different distributions.
Yes, those are different
And
distributions.
what do we mean by fitting?
Fitting the data.
Fitting the data.
Fitting the data. So yes, this is not a thing that you've heard up to this point. This is a new idea. So let me actually back up, because there are multiple ways that we can talk about what the word fit means in the literature. And some of these are synonyms and some of them aren't. So one way that people talk about fit is prediction. Like, I've heard people say that R square is a measure of fit for a model. That is not true. It's prediction, in the sense that fit describes what should happen versus what actually happened to a set of information. So prediction and fit are not the same. I know, it's confusing. It is, I'm not lying. So in categorical data, there are sometimes likelihood ratio tests used to compare models with predictors against models without predictors, where they're trying to figure out what the right answer is as a saturated model. They fall into this category. We're not going to deal with those because there's only certain situations in which they're useful. When we get to multivariate models, and for those of you from the factor analysis class, crossover event continues, fit refers to the match in the data relative to what the model says with respect to the moments of the data. So we're talking in multivariate models about the means of our variables, the covariances between variables, and the variances of the variables in the data. And then we have a model that says, I think they should look like this if your model is accurate. And fit is how far off the two are, the mismatch between the two. So in this context, this is a precursor to deciding whether or not we want to use the model to make predictions, is because the model has to fit the data. It has to adequately represent the data in the first place. In single level regression, like when you have one outcome, this is not a thing, because why does it keep flickering? Each outcome is going to get an intercept and a residual variance, and that means the mean of the outcome and the variance of the outcome are going to be captured just fine, and it's not a concern that you have. So this is a concern in multivariate models, and it is a concern in generalized models where we're not sure what distribution we should use. So this is an empirical way by which we can say, does this distribution actually look like it fits the data? Does that help?
Yeah.
Well, yeah, it's a fuzzy thing. It's fuzzy. So it's basically asking, like, empirically, I fit the model, I have the numerator is a residual, like how far off your prediction is. And on average, like, you would expect that to be like a standard deviation. And this is what the model says the standard deviation should be at this point. So for instance, if this is Poisson, and I have a predicted mean of 5 on the count scale, then the standard deviation should be the square root of 5. because in Poisson, mean and variance are one number. So mean is 5, that means variance is 5. The standard deviation should be the square root of 5. To the extent that it's not the square root of 5, like on average across people, your model's off. There's more variance in the data than is expected by the model. So your model is not adequately representing the variability. It's variance that we're concerned with in this case. So this is not available everywhere, but I found the places where it is. In Stata, it is available via the GLM, Generalized Linear Model, sort of generic package. It's not available within the specific versions. I also found something that a user created called CountFit that has it. And in R, I found code to do it manually, meaning compute it yourself. Not like on a calculator, but writing code to compute it out of the saved results. That's manual as I get. So side note about that, we'll leave that alone for now. So in the textbook that we're using, which is a Stata book, but it's much more general than that, they list how these things are computed for all different kinds of distributions. So we have Poisson as one that we're interested in, and negative binomial as another one. And note that all of these things have a numerator and a denominator part, which means what actually happened in the numerator divided by what should have happened in the denominator, except this one, Gaussian. What does Gaussian mean? Normal, yes. That normal distribution, it doesn't have a denominator because the variance is separate from the mean in Gaussian. So the first time that I taught this class, I did not realize this, and I used this number to judge the fit of normal distributions incorrectly. Oops. So that was the 2020 version. So if you see that anywhere in like old slides, just disregard it. I screwed it up. I'm sorry, I'm imperfect. This is what happens when you try to teach a class during the middle of a pandemic. Things start to go a little sideways, especially when you're homeschooling your preschooler. That was what I remember from that semester. My son was not having it. He turned 5 on March 7th. The world shut down on like March 11th, and then I became a stay-at-home mommy / generalized linear model. And it turns out I am very bad at stay-at-home mommying. So I'll blame the pandemic on that, but normal distribution does not play by these rules, is what I want you to remember. It's these other ones all have a way of getting to this. So we are concerned about this summary statistic of distribution fit being larger than 1, which represents a term called over-dispersion. That means too much variance relative to what the model is expecting. Too much variance in the data. All right, so let's see this in action. I'm back in example 3, which we started before break and revisited on Tuesday. Do you remember the story about this? Real data. The outcome that we are predicting is the number of aggressive verbalizations in an experiment where people were deliberately pissed off in various ways to be aggressively verbal. You will hear me say this as a count of the number of mean things people said, for short, because aggressive verbalizations is a lot of syllables, especially when I only brought water to school today. And the first model that we looked at last time was a standard ANOVA, which means what kind of link function in a standard ANOVA, in a general linear model? What kind of link function is used? You're like, is there one? There's not one, but it has a name for not one.
Identity?
Identity, yeah, times 1. That's the link. That's how general models fit under the umbrella of generalized. Which is funny because the term general linear model, I believe, was coined by Jacob Cohen. Like there was an article in like 1950 that showed mathematically how regression and ANOVA were the same thing, and at the time that was news. And so at the time it was like, this is the most general thing I can think of. I'm going to call it the general model. And then a few years later, people were like, actually, this is just a subset of other things, so we're going to call it generalized. And then, you know, there's going to keep being more umbrellas on top as time goes on, and they're going to have to make up new words. But general is a subset of generalized that has an identity link and a normal distribution as the conditional distribution. So we can switch out both of those things as needed to fit different kinds of data. So we looked at that, and the p-value for the interaction that was near and dear to the student's heart was 0.06, which I'm pretty sure is why I got involved in the project to try and help that. And it looked like only one of the interaction contrasts were different. The difference between this red line and this blue line right here. Basically the effect of cognitive reappraisal as a strategy for dealing with being pissed off versus suppression. Cognitive reappraisal is better, results in fewer mean things said, but differentially so for people with a history of IPV in the red versus not in the blue. So this picture is the story, right? What we're doing is trying to come up with an accurate representation of the story in terms of the inferences. Which of these differences are significant and which are not is a function of what the standard errors are, which is a function of what the distribution is. So we're all working backwards to make sure that we can say something reasonably accurate. So let's look at log link and Poisson as an alternative, since this is a count outcome. So the model is exactly the same. Generalized model, in StatF to start with, and then I'll show it in R as usual. Using maximum likelihood, it wants to know what kind of link you want, log, what family, it means distribution by that, Poisson. And no log, by the way, out here just shortens the output. So it shows like the iteration history of the estimator, and it just takes that out of the output. So this, I realize, could be confusing because I'm like, I thought you said log, and now it says no log. Well, no, this log refers to the link function. This log refers to the output, and you're just supposed to know that. Job security. So here's what we get then. The first thing I want to point out to you is this new quantity right here. This is my index of distribution fit, the Pearson chi-square over degrees of freedom, and it's 4.7. So that means roughly there is 4 times as much variance in this outcome as what a Poisson model would predict. To say that differently, we are under-predicting the variance. So that's not good. It tries to help you by saying, what is my variance function? V of mu equals mu. That's status speak for the mean and the variance are the same because this is Poisson. Likewise, link function G of mu is ln mu, which means natural log. So in some software it's ln for natural log, and some it's log. Just got to look at the documentation to see. So practically speaking, what do you think the consequences are of us having not enough variance in the model relative to what the data have? If we are under-predicting how much variance there should be, how could that show up in wrong conclusions? What about the coefficients themselves? Are those going to be affected, do you think?
I might just be thinking about it in a different way than you're trying to get us to answer it.
Sure, it's
But
possible.
my first thought is that there would be possible confounding factors that we're not taking into account, which has a potential of influencing coefficients, even though it doesn't necessarily mean that it will influence them too much, but there's a possibility of it.
You mean like omitted variables?
Just not necessarily omitted in the sense that we measured it and didn't include it, but there's some possible other external factor that we're not taking into account that could account for more of the variance.
I think it's a question of, I think that is true, but it's not where I was going.
Okay.
Where I was going is, like, our job is not to, okay, actually, this ties to your question. This is good. This is a connection I wanted to make and didn't get there. So thank you for the opportunity to get there. So you're talking about prediction in terms of fit, like that we're missing information that should reduce the variance. We don't have it and the variance is too high. But what I'm talking about is quantifying how much variance there is to be predicted at all,
Okay.
which is a distribution fit, which is what we're concerned with here. Because we have to have an accurate measure of variance in order to say how much of it we got. And in these models, there's not a single number that we can come back to as my variance is 10, like there is in the normal distribution, because it's not a separate thing. It's tied to the mean. So in this case, let me give you the answer, essentially. Where's my little indicator? Here we go. I showed this last time. Remember this table? The green columns were right here. So these are predicted means from the model parameters. They are exactly the same. So the slopes themselves are fine. Other than the fact that they predict the log of the expected count and not the raw count, the slopes are fine. But the pink parts, what do you notice about the 4 columns here with respect to the pink and red parts? They're all different. And Poisson in particular, much smaller. Yes, smaller standard errors because our model is saying that we don't have as much variance. The variance is tied to the mean directly in Poisson. So that influences what it thinks the standard errors would be. What do standard errors tell us more generally? Like definition-y? Like think back to IntroStat. What does a standard error tell you in the first place? Like if this is the standard error of this mean, what does it tell me about this mean?
The variance of each data from the mean and the actual data.
So are you talking about people or are you talking about samples?
Ooh,
Yeah,
it's confusing.
it is confusing. I spend like a month on this in the first class.
So, in the realm of samples.
It's
that
samples.
If we were to keep resampling, we would expect the mean of those samples to fall in a range around plus or minus 0.23 of the mean we observed.
Yeah, so that would give us like 67% of the samples or something. If we go out to 2 standard errors or so, that's 95%. You can build intervals, yeah. So let's go through this here. So standard deviation for this condition this is about the people. Standard deviation is how far off any one person is from the mean. And each of these different types of people, in terms of what condition they were assigned to and their history of IPV, has a different standard deviation because each of their distributions is differentially wide around the mean. That's one piece of information. That's people level, though. If we go up to sample level, then this standard error here conceptually is like a standard deviation. It describes the dispersion not across the people, but across repeated samples of people. So a standard error tells you the expected imprecision of that mean across repeated samples of the same size and kind. So like 0.23 is how far off this mean estimate would be in any one sample on average relative to the population mean that we'll never ever know. We don't know the population mean and we just sort of go with that. Right? We don't know what the right answer is. Only in simulated data do you know what the right answer is, which is why simulation studies are useful in quantitative research. Right, Vladimir? Right, Erica? They're learning how to simulate data. It's fun, isn't it? You're like, sure. Let me tell you this. When you get to the point where your program actually works, you are going to jump out of your chair and do a dance of joy. It's going to be a magical moment right there. But until then, it sucks. I understand. But creating data can teach you a lot about these things in ways that are different from a classroom environment. But point of the story. This is describing how wiggly these means are expected to be across repeated samples and sort of how much faith we have in them. So the fact that all of these standard errors are lower is giving us a sense that, oh yeah, I know what this mean is. It's 2, as opposed to like 2? And these standard errors are a consequence of what the model predicts the variability around that mean to be, which is a consequence of the distribution that we choose. So I could be like, hey, these ones are smallest. I like this one best. But liking which result comes out in your favor is not the right way to choose a distribution. So going back to the output then, standard errors are the standard deviation of the sampling distribution. That's how I can tie the two together. But anywho, each of these coefficients will be fine. It's the standard errors that go with them that are a function of the distribution. And in contrast to our previous model, everything is significant here. Like there was nothing significant before, especially the interaction terms, and now they're significant to the third decimal place. So it's like, should I report this model? Because the p-value that my student desperately wanted to be significant was 0.06 before in the normal distribution, and now it's 0 to 4 decimal places. So do we believe this or not? This is where this comes into play. My distribution fit index, Pearson chi-square over degrees of freedom. This is an index of what the variance is in the data as observed relative to what it's supposed to be according to a Poisson model. And this means we have 4 times as much variance as we're supposed to. So this is not believable yet. Not yet. Which is too bad, because everything is, wildly significant. Now, folks in R, you're going to have to work a little bit harder. I know. I don't make the rules. Take it up with the rest of my program who insists on using R for everything. And the rest of the world, for that matter. So there are differences across packages in how this statistic is computed and what it considers degrees of freedom to be. In some packages, it's based on sample size. And in some packages, it's based on sample size minus the number of estimated fixed effects. So the first thing I had to do in R to reconcile this across Stata and SAS, which do it differently, is create 2 placeholder variables for what degrees of freedom is going to be in this model. I have 225 subjects. I have that minus 6. So SAS, GenMod, and Stata use this version, and SAS Glimix uses this version. So when you see differences, this may be one of the reasons why. So I'm going to fit model Poisson here using GLM. And family is Poisson with the log link. The formula looks exactly the same. And I'm asking for a summary. And here's the same estimates that Stata gave us. And note this thing right here, dispersion parameter for Poisson family taken to be 1. That's referring to the K-stretchy factor, essentially. However, it's not quite that simple. ... Stay tuned. It's on a different scale in R. So I had to ask it to come up with my Pearson chi-square index of fit by doing this function, the sum across everyone in my data set of the residuals that were saved from the object model Poisson from my model. I asked it for Pearson, and then squared that, and then divided by the degrees of freedom as used in Stata, since that's the output I'm trying to match right here. So this part is done for you in terms of something that's built into R. You just have to wrap it around this to get to the full statistic. Sum across persons squared divided by degrees of freedom, and there's the 4.7 number that we saw before. Here are examples of joint hypothesis tests, because these are also no longer provided. So here is a test of the model R square, whether the 5 slopes that I have work together to create a significant prediction. And survey says, yes, they do. Here's the test of the interaction, so lumping together just the 2 interaction slopes to get a joint hypothesis test. So this matches what we found in Stata as well. Here's some predicted outcomes. First, in type equals link, so I'm using the function prediction from the prediction package, and I'm telling it what values of my predictors I want the predictions to be generated for. So this will be a range. And type equals link, can you guess what that does? What scale are these predictions going to be in? And feel free to read from the screen too, that's always an option. Yeah, log, in the link, in the model version. So these are in logs. So using the model slopes, it came up with these predicted log of expected count. And you're like, can you just give me the right answer in counts? Yes, I can. I did the same thing asking for predictions where type equals response. So that is in the inverse link, going from model scale back to data scale. So this will be in expected counts instead. So people in this condition are predicted to say 2.7 mean things on average. People in this condition are only predicted to say 0.15 mean things on average. And then this condition are the troublemakers, 4.5 mean things on average. Now, can I say 4.5 mean things? Like, is that possible? Maybe I say 4 mean things and I get started on another, but I change my mind mid-sentence. 4.5? Yeah, backhanded compliment? Yes. I'm surprised you did so well considering how stupid you are, something like that, right? That's like half. So I'm making this point to keep in mind, these are expected counts. These are not raw counts. Raw counts are only integers, but expected counts can be in between. So that's why I keep saying expected count. And if you're like, can you just say count? It's fine. If you just want to say count, I'm fine with that. This is a distinction that I don't know that it matters as much, but I'm trying to say it correctly. Say that again? The raw count, so in the data, I only have integers because you can't really say 4.5 mean things. But in terms of what the model is predicting for the expected count in that condition, it's 4.5. Expected counts are continuous. That's the point I'm trying to make. Yep. So then we go through the same series of simple effects. Do we want to go through this again? What if I told you your next homework is going to have interactions in it? Like, damn it! I knew that homework 3 was too good to be true. Okay, so we have red versus blue here. Blue is the no IPV group. Red is the yes IPV group. In terms of the model coefficients, the first 3 here, the 1 is in the spot where the IPV slope is. So that tells me I'm asking for the IPV slope. Then who am I asking for it for? I leave out the next 2 are for the main effects of group. They have nothing to do with the IPV slope, so we leave them out altogether. Note they're zeroed out all the ways. Instead, what I do is use the interaction terms, and I put a 1 for the group that I want the IPV slope for. So it's 0, 0 for the reference group. The first interaction term turns on if I want the cognitive group, and the last interaction term turns on if I want the suppression group. So which of these did I actually need to write, and which of these did I not? Let's go, which of these did I not need to write? The first one. So as a general rule, if you're asking for any kind of comparison or slope that relates to a reference group, it is already in your model. If you're asking for any kind of comparison between alternative groups or simple slopes of some predictor for an alternative group, you got to ask for that. So if you get done with one of these statements and you realize there's only one 1 in it, you already have it. Now, I do this for pedagogical purposes plus for my own sanity. Because the you that looks at this like 6 months from now is going to appreciate having everything in one spot in the output. By the way, I did not learn how to do this until I was already on the tenure track. Do you know what I learned how to do instead? Recode it and rerun it. So if I want to know the slope for the cognitive group, for instance, I make a new version of the model where the cognitive group is the reference, and then I get the slope for the cognitive group. And then I do it again for the next group, and again for the next group, and again for the next group. It's tedious, but it will work. I once had a person come up to me after a workshop where I showed how to do this, and she said, I just spent like all these days rerunning the same model like 90 times to get the slope for all these different groups. I'm like, I'm so sorry. But I want you to be able to do this. Linear combinations to answer different questions. I'm sorry? She was trying to get some estimate of something for every single unique value in her data set. And that was how she knew how to do it, was to recode it into 90 different versions and run the model 90 different times to get the one number that was unique to each. It will work, do not recommend. So this set of simple effects then are telling us about the effect of IPV. And they are telling us about the vertical distance in the no group, the cognitive group, and the suppression group. In those groups, it looks like IPV is higher in the none group, so red is higher than blue. In the next group down, red is lower than blue. And in this group, red is higher than blue. You can see that visually, but here are the numbers that go with it. And then if we look at the inference, according to the normal distribution, only the last difference is significant. According to Poisson, both of the last ones are. Okay, next set. None versus cognitive and none versus suppression. The none group is the reference. The IPV group is the reference. So did I need to write these two lines? Nope, there's only one in each. That means it's already directly a model parameter. The one that I need to get is this one, the difference between the non-reference groups, specifically in the IPV no condition. And so to get that, it's -1 and 1. So this will almost always be true. If I ask you to find the difference between two things, and one of them isn't the reference group, do this instead. I'll show you why. It's backwards, but actually let me make it not backwards. 1 second, let me get a new one. And I'll paste it in there because it's easier to see it that way. Here's why. Okay. I want, oh, darn it, I grabbed the wrong one. Un momento, por favor. I wanted these two. Okay. So I want to answer the question of how the two alternative groups compare. And this is the order in which I need to have them, because I want to have the cognitive group as the reference for this comparison against the suppression group. So that means suppression comes first. So if I'm going to build this from scratch. This is going to be cogger versus sup. What's up? What's sip? What's good? Jonathan tries to be clever most mornings, and instead of saying good morning, he says, what it is. Because he told me that's a slang term. And so I'd like, all right, where it went. How long is it? I don't know how to answer that question. What it is, folks. Sup. Okay. So let's fill in my things here. If I know how different the sup group is from none, and I know how different the cogger group is from none, then I literally just subtract to find the difference between these two. So what's 0 minus 0? Not a trick. What's 0 minus 0? What's 0 minus 1? What's 1 minus 0? And then I space these over because it makes my life easier. There. That's how. So it is not a coincidence that I always will ask you homework questions of what is the effect in this group, what is the effect in that group, and what is the difference? Because if you get the first two right, you have the ingredients to get the difference. You just have to literally subtract. Where's my other one? So that's why this one is negative. Let's do these ones. This is in the alternative group for IPV. So there's more stuff in it. Okay. Same principle. Cogger versus sub. So in this first one, if I want to know what is the difference between none versus suppression for the other group of the interaction term, well, this much gives me the main effect of none versus suppression. That's the second main effect of the grouping variable. But to get to what it is for the other group of the moderator, IPV equals yes, I got to turn on the interaction term. So this is a simple slope for the other variable being turned on as a moderator. And the same idea with the difference between none and cognitive, that's the main effect. That's what it would be if IPV were no, like it is up here. But to get to what it is for IPV yes, I have to turn on the interaction term. And so then to get the difference between these two, we end up with the same pattern. Like that. So if you just look at this in isolation, you'd be like, where the hell did that come from? But it came from the ingredients. And once you've done this enough times, you can just start to see the patterns and fill them in. But until then, I would encourage you to just literally subtract. And make sure that the order is such that the one that you want to have as the reference is second. So in this case, like I want it for the cognitive group as the reference point, then that means that that comparison is second in terms of what's being subtracted. If you get it backwards, you will get the right coefficient, but the sign will be opposite. So I would always encourage you to try that in your homework too. If you think it's right, flip the sign and see if it's right. That just tells you that you wrote it in the wrong order in terms of which is the negative one and which is the one. Okay. Last but not least, so these ones, by the way, are the red slopes, the blue slopes, and then the implied differences across the first and third columns here. Now the interaction terms. There are 3 interactions implied by this model. And I can talk about it 2 different ways. I can say, to what extent does IPV matter differently in this group versus that one versus this one, or this one versus this one? Or I can talk about how does the effect of the experimental manipulation in terms of this comparison differ as a function of IPV history. Either of those is correct. And sometimes in homework, I will ask you the same interaction term both ways just to get you to recognize that. So which of these are given by the model, and which do I need to ask for? I just have to ask for the last one, and that's because these all involve the none group. That means they're going to be in the model, and you can also just look at this. If there's only a 1 in one spot, you already have it. But the last one is the -1, 1 for the same reasons that we just did. So you have to do 0, -1 to get the order right. Okay. Feeling a little better? Maybe? I think of these things as like magic eye posters. Have you ever seen those before? Like there's like this poster with a whole bunch of stuff and you're supposed to be able to like see something in 3D if you stare at it long enough. Ironically, I cannot see those posters. Like that's not within my capabilities, but I liken it to like once you see the sailboat or whatever's in the middle, you can't unsee it. Once you see the patterns, it will just lock in, but it takes a very long time to get to that point. Okay, but we don't like this model. This model doesn't have enough variance. So let's switch it out and add some stretchy. Negative binomial. So we are changing the link function or the distribution. Distribution. We are doing that to try to find a distribution that allows for overdispersion, where the variance can exceed the mean. So I'm doing this in two different ways in Stata on purpose. First, I am using NBReg, which is negative binomial regression. It does not have any index of distribution fit to it that's done for you. What it does have is this thing down here under the output, which says LR test of alpha equals 0, chi-bar 201. Clear as mud, right? That's a Midwestern phrase for you. Okay, so let's break down what the hell are they talking about. First off, they give you this thing, which I have labeled as the log of k. So they give you the natural log of the stretchy factor, and then they give you the k version of it too as alpha. Because, you know, we don't have enough things that are already called alpha in our life, right? Alpha is type 1 error rate, alpha is reliability. What else is alpha? There's like 7 things that are called alpha. Like, fine. K, on the other hand, is not as many things, but more than one. So part of the difficulty in figuring out what your software is telling you is which version of stretchy you're getting. So what this is doing is testing the version that corresponds to the notation of this version, where if k is 0, then the second part of this drops out and it becomes Poisson. LR test, you know what those words mean, right? Likelihood ratio test, difference in -2 log likelihood. A recurring theme. So this is testing directly whether the likelihood of the negative binomial model is taller than the likelihood of the Poisson model. The probability is 0 to 3 decimal places, so the answer is yes. This model fits better. The O1 part in here, I don't think we've talked about this yet. Mixture chi-squared, does that term mean anything to you? Nope? Okay, good. There are debates in certain cases about these kinds of model comparisons as to what reference chi-square distribution you should use. This is one of those cases. So to be most correct, meaning to not have like some statistician reviewer 3 yell at you, you should use a mixture chi-square. What that means is that this k is logically bounded at 0. It can't go negative. So that means if you think about the sampling distribution of what k could be across repeated samples, like it can't have a normal sampling distribution. It can't be sometimes positive and sometimes negative with a null hypothesis of 0. 0 is the boundary, and 0 is the null hypothesis. So there are various situations like this. If you're testing the addition of a variance, variances are lower bounded at 0. If you're testing the addition of a correlation of 1 versus something else in SEM, correlation of 1 is on the boundary. So in this case, the proper reference distribution is a mixture of chi-squares where degrees of freedom 0 for the times k wanted to go negative but isn't allowed versus 1 when it is positive. Chi-square distribution with degrees of freedom 0 is not a thing. It's not. It's 0. So this is a very, very long-winded way of saying take the p-value from a regular chi-square and cut it in half. That's your mixture chi-square in this case. So Stata is doing that work for you. Not that you can tell. The critical value that you would use switches from 3.84 if you do it the lazy way with the straight up chi-square degrees of freedom 1 versus 2.71 if you do it the right way. So 2.71 is a cutoff versus 3.84 is the difference in using a mixture or not. Only in the situations where it's in the middle should you care. But that's what this chi-bar means. It's a mixture chi-square instead of a regular one. So negative binomial wins, but we don't yet know if it's any good. We know that it's better than Poisson. So that I had to rerun the model using GLM instead. So it's the exact same model, just a different function within Stata, so that I can get the distribution fit index. And it is 1.12. I'm going to call that good. Like, that seems pretty damn good to me. Note that in the variance function over here, it's still trying to help you in its own Stata way. The variance function is this. 1.601 is the estimate of the stretchy factor of k that allows the variance to grow as a quadratic function of the mean. So if this number were 0 instead of 1.6, we'd just be having straight Poisson. But this allows the extra variance. So if we look at the results, the coefficients again are exactly the same. The mean differences between the groups are still the mean differences. The question is, do we believe them? Now we get more of a heterogeneity with respect to the simple effects. But the interaction term is still decidedly significant. And I will tell you that as far as my student was concerned, this is the end of the story. She wrote it up, she turned it in, she got her master's degree, got a publication out of it, and eventually graduated with her PhD and got a job, and is now living happily ever after. I don't know what she's doing, but I will tell you that in the future, if you ever just like drop me an email and let me know how you're doing and where you work and how life is, I would love it. It's so weird to be like, get to know everyone for, several years and then you go off into the world and I never hear from you again. It's so weird. So, yeah, write to me. Rosie, if you're listening, write to me. So that was the version that got reported. Here's how we can do the same thing. Actually, no, a few more things in here. Because we're back to variables that are numbers, I'm going to do an R-squared the old school way. Do you remember R-squared in logits and probits and stuff? It wasn't a thing. Like there were 18 ways you could compute it. I'm going to compute it for real. There are two different definitions of R-squared that you may have learned in standard regression. What did you learn one of them is? If you had to define R-squared in a standard linear regression, what does it tell you?
Yeah.
In stereo. How much variance? Explained by the model predictors, right? Yeah, that's the version that I think is most intuitive. But here's another one. If I take my outcome and I build the predicted outcome, we usually call that y hat, we're calling it mu in this class, and I save that predicted outcome to my data set. These are the columns of my data set, that's why we're doing it this way. It's not like football, not like Touchdown Jesus or something at Notre Dame. This is columns of my data set. If I take my real y and I correlate it with my predicted y, that's r. And you know how I get to R-squared? I square it, that's right, and that's R-squared. So that's another way to think about R-squared, is how related the predicted outcome is to the real one. And if you think of it that way, it makes sense that you would have an F-test for whether R-squared is significant. Like, is the outcome that you predicted related at all? That's a hypothesis test, and then how related is it is R-squared. So I'm going to borrow that same technology and predict a new column in my Stata data set called pred count, correlate it with the actual number of mean things that someone said, square that correlation, and ask it to print it. So 11% of the variance is explained by IPV, experimental condition, and their interaction. Lots of other things out there. Lots of other reasons why someone might say mean things. And in the original publication, there were X, Y, and Z covariates that were controlled for because of those reasons. And I decided to simplify the story for present purposes because this handout was already 15 pages long. One of my shorter ones, actually. Also, because the world likes effect sizes, E form is how you get it to give you odds ratios in Stata for GLM. They're called incident rate ratios, but they're the same damn thing. All right, R folks. This was a challenge. I went through many different permutations of R packages and functions and finally found something that behaved in a way that was acceptable to me. But this was a challenge. Have you been through this challenge before?
Not for this type of analysis.
But just in general, right? I went through 8,000 permutations until I found this one. So this is from the package called MASS, which has a number of useful features. This is glm.nb is the function that does negative binomial. And it gives you an option for what link you want, but it doesn't give you any distribution options because it's NB, damn it, that's what it's called. Like, this is your choice. So this one gave me coefficients that matched the other packages, and then it gave me this thing. Dispersion parameter for negative binomial is 0.62, family taken to be 1. Okay, no, it's not taken to be 1 anymore. Stop it. That was what the Poisson model output said. But then this number is not 1.6, which is what I was looking for. So then I figured out after considerable trial and error that it's the inverse. It's 1 over k, just, because this stuff isn't hard enough as it is. So depending on your software, you're either going to get k, log k, 1 over k, or 1 over log k. Those are the possible choices. Either way, you can do a likelihood ratio test to see whether k needs to be there or not. So then I found somewhere in the bowels of the output, I found the actual version of k. So there's the 1.6, and I asked it to print it. Here are the distribution fit measure. This is Pearson chi-square over degrees of freedom, the 1.12, which we agreed was pretty darn good. And then I ran into another problem. I wanted to do a likelihood ratio test to compare the Poisson model with the negative binomial, like Stata did for me. And R's like, nope. ANOVA, I even tried RANOVA, that's another one I know, and it's like, nope, these are from different packages, I'm not doing it. All right, I'll do it myself. So I made my own test statistic by -2 times the likelihood from the Poisson model minus the likelihood from the negative binomial model, and it always is in this order, by the way. It's fewer minus more. Then I found the p-value using a function called p-chi-squ with div test with degrees of freedom 1. And then to compute the mixture version of it, I divided that by 2. So then when all is said and done, here's my test statistic. Here's the original p-value that statisticians will tell you is not right, and here's the one they would prefer. And it's e to the -75. Do you know what that means? This is scientific notation. It's 0. Like it's really, really 0. 0 to 75 decimal places or something like that. So yeah, if you get scientific notation on your R output, it's 0. All right, so then I did the usual hypothesis test. Interaction term is still significant, so hooray, hooray. And then I did the same step in terms of computing an R square. So I built a new column in my data set out of the predict function. Type equals response means save the predicted counts, not the log counts, but the count counts. And then I correlated the two of those and squared that correlation, and I end up with this. So same answers with respect to that. All right, so then here's the comparison of all the results. And it's the last column that so far looks the most trustworthy. So far. However, let me go back to the picture at the very beginning of the story. This picture. There's a vocabulary word that we talked about with respect to this picture and the number of zeros in it. So Poisson can fail in 3 different respects. You can have too much variance, it could have no zeros, or it could have too many. Yeah, this is formative assessment questions. It's all coming back together again. What is the technical term for too many?
Zero inflated.
Zero inflated. So that's the last thing I want to look at is to what extent does the model adequately predict the number of zeros that I have, or do I need to add something to it to do that? There are two different versions of models that address zero inflation. So let me describe how they work. Actually, one stop in the middle briefly. This is slide 13. We didn't talk about this yet, but if you have no zeros, then you pick a version of the Poisson or negative binomial that it does not have zeros in it. It is called zero altered or zero truncated. And it essentially rearranges the probability function so that it still sums to 1 without 0. So you just pick these options instead, and you're good to go. That's going to be needed to address zero inflation in just a second. So there are two options for what to do with zeros. One is to try to distinguish which zeros are expected based on the distribution, and then separate them from the zeros that are unexpected. And the term unexpected is called structural zero in the literature. And this is the idea of mixing populations together. Like if I ask you, let's see, what's my favorite advice today? How many episodes of Grey's Anatomy have you watched in your lifetime? Who has never seen a single episode of Grey's Anatomy in their lifetime? Okay, structural zeros, you're dismissed, right? You don't know good television until it hits you. But the rest of us may be Grey's Anatomy fans to some extent, right? How many episodes have you seen, would you estimate? Those of you who've seen Grey's Anatomy. There's only like 7,000 of them, so.
I'm close to almost the final season.
Yeah,
So
you're working your way there? Yeah, I've seen every episode, and now I'm rewatching it, and I'm halfway through season 10, so I'm very invested in this. I'm the end of the distribution, right? But among the Grey's Anatomy watchers, right, there's some distribution of number of episodes that you've made it through, at least once. So this idea of a zero inflated model is me like, okay, let's predict the logit of you being a Grey's Anatomy not watcher, or the number of episodes among the watchers. And the key thing that makes this weird, in my opinion, is that the count model still includes 0. It's still predicting the count of events using either Poisson or negative binomial, including 0. And then there is an extra submodel where we are predicting the logit of the probability of being an extra 0. And you're like, hey, Lisa, how do I know if a 0 is extra or not? Hell if I know. Nah. So then you can try to predict who is likely to be a structural 0. But good luck writing this up, honestly. Like trying to explain the difference between an expected 0 and an unexpected 0 is, to me, very theoretically challenging. I've got, here's the picture that I've showed this before. This is the number of steps taken towards divorce in couples. And here is the overlay of the predicted distribution estimated. The parameters of the distribution are making these lines essentially under different expectations. So Poisson is the solid gray line here. That's this one. It doesn't work. Poisson expects there to be a whole lot more people right here and a whole lot less, people in the 0 pile. So a zero inflation Poisson would be like, I can fix that. Watch. I'm going to make all of these people from the top of the distribution in reality to where it's supposed to be, you're all extra zeros. So it's predicting like the amount, essentially. And negative binomial, the original version of it is right here. So negative binomial builds in the stretchy, which better accommodates the fact that we have more observations out here, fewer in this section, but it predicts the zeros should be here. So then zero inflated is like, hey, I can fix that. All y'all are extra. And so then the zero inflated versions are like, okay, I'll just build that into my submodel, and now we have this line going like that. So we can ask, do we need this extra submodel? What is the logit of the probability of being an extra zero? And you can just estimate an intercept only, or you can actually throw predictors in there. So let's look very quickly at that, because it's not going to go well. And then we'll go. I don't know if we have time. We'll talk about hurdles maybe later. We'll see. Here we go. Okay. Yeah. 3 more things. So in Stata, I used a package called ZIP, which stands for Zero Inflated Poisson, and then added in the inflation model underscore constant, which means only an intercept. So the logic is an empty model says everybody has the same probability of being an extra zero. What is that probability? Is it 0.0000 something, or is it like, 0.2? How much do we need it? So we get an inflation factor in logits, because this is a binary outcome we're predicting, whether or not someone's extra. And we can convert that logit into probability, which is 0.37. According to Poisson, 37% of my sample is extra zeros. Ooh, that's a lot. But Poisson didn't fit that well. So here's what it is in R. They came up with a very comparable number, about 37%. I tried to add the zero inflated negative binomial version, and Stata threw up. Technical term is we encountered model non-convergence when attempting to estimate a zero inflation submodel. Threw up. Blew up. Also accept that. So I found in a whole nother package, PSCL, someone else's thing. This is like a scavenger hunt to find all this stuff, I swear to God. Zero is the name of the function. And this part right here after the bar is what you want the the zero inflation submodel to be, and I only want an intercept. So it came up with, oh, and by the way, the stretchy factor is labeled as yet another thing in this package. It came up with a logit of -11. Now, in your knowledge of logits, how much is that? Yeah, it's very, very close to 0. And in fact, it is 0 to that number. That's what a logit of -11 is. So point being, negative binomial was a better distribution fit. So we're going to go with that. We can ask the question, do we need to worry about extra zeros? And this model tells us the probability of being an extra zero is 0.00000. So no, we don't need to worry about it. We can also do a model comparison, but this is sufficient information. Stata has a routine, by the way, that will run all of these things for you and do the comparisons for you, like that. So this thing, count fit, you can list which ones you want. I did Poisson negative binomial and zero inflated Poisson because I knew that zero inflated negative binomial was going to throw up. And then it does all of the model comparisons for you. It also shows predictions. So this is a plot showing the number of aggressive verbalizations, like what actually happened on the x-axis, and then the discrepancy, how wrong the model is on the y-axis. And so the Poisson model is the blue line, very wrong with respect to the number of zeros. So here's the 0 line where right would be. The negative binomial is the red one, a little bit bumpy, but not too terrible. And the zero inflated Poisson gets the zeros right, as well it should, that's its only job, but gets the rest of it wrong. So based on this evidence and the probability of being an extra zero in the 4th decimal place, then I would say it's negative binomial, write it up and turn it in. There. We'll get to the other way of doing this next time, but it's called a hurdle model. Have you heard that term? No? You're going to learn it next week. All right, any questions as we wrap things up today? For now, I should say.
So does that all mean that every time we are dealing with count you're not doing like, see the difference with eyeball, but to run the actual number analysis to
Yeah.
decide which one to use.
Yeah, I think that there's various ways to decide. Like a picture like this, I think should support the conclusions that the model comparisons. But if you have something that's sort of like on the fence, then maybe this information would help you decide between the two. In general, I would say you go with one, but then you cover your bets, so to speak. Like, I ran the model this way too because this way could have fit, but the results were the same, so therefore I only report this version. That's your footnote that gets you out of that. All right, other questions? I need to go pick up my kid too, so it's a good place to stop. All right, thanks for being here. Have fun on homework 3. Let me know if you need anything. See you next week. Bye, Zoomers.